So here we have a situation where the population of a city is being tracked over the course of 90 years. They're taking the data from the 10-year census and fit an equation to this data that is given here, a logistic regression equation. So this is the function that models this data, and we want to use this equation to determine the year in which the population is growing the fastest. So this function here gives you the population based on the years since 1910, which means that when we're looking for the population growth, because we want to know where the growth is greatest, well, the growth of the population is going to be the instantaneous rate of change of the growth. In other words, y prime is the instantaneous growth This is, of course, what we are trying to maximize. And so to find the extreme of a function, we can use the first derivative test, meaning that if this is the function I'm trying to maximize, I'm trying to find where the growth is greatest. What we're going to do is we're going to take the derivative of this function. So we'll use y double prime and first derivative test. To find the max of y prime. Okay? Alright, so with that being said, we now need to go find the first and second derivative of our logistic regression equation. Alright, so I'm going to give some variable names to the constants that I don't want to rewrite over and over again. And this is going to allow me to rewrite my equation as y equals 4930.829. And then I'm going to bring the denominator up into the numerator. So it'll be 1 plus a e to the b x all to the negative 1. And now when I take the derivative of this, it's not going to be nearly as painful. So y prime, using the chain rule, I factor out this constant. Using the chain rule, I will have negative 1 times 1 plus a e b x to the negative 2 times the derivative of the inside. The derivative of 1 is 0, and then the derivative of a e to the bx is going to be a e to the bx times the derivative of bx, which is b. Alright, so let's go ahead and just reorganize this a little bit. I can bring the negative 1 out front, and then I'll have a e to the bx times b, which is just ab e to the bx. And there we have our derivative. Now we want to take the second derivative, because remember, this is the function that we're trying to maximize. So we want to take the derivative of this function. Now to do this, remember, we can keep this constant out front, and then here we just have two functions of x, and so we can use the product rule here. So I'm going to go ahead and set up the product rule to take the second derivative. Alright, so here we have ab e to the bx times the derivative of this here, which is negative 2, 1 plus a e to the bx to the negative 3, times the derivative of the inside, which is a e to the bx, times the derivative of bx, which is b. So it'll be a b e to the bx. Then I have the derivative of this here, which is, of course, ab e to the bx times the derivative of bx, which is b. So it'll be a b squared e to the bx times this function here, which is 1 plus a e to the bx to the negative 2. All right, so at this point, I want to look to factor some things out. And what I can factor out here are a couple of things. I can factor out an ab e to the bx. And I can also factor out a 1 plus a e to the bx to the negative 2. And so what I'll be left with is a negative 2 a b e to the bx and a 1 plus a e b to the negative x to the negative 1. And then over here, I'll be just left with plus 1. Okay, so there's what we have left over. And what we need to realize at this point is that this is our second derivative. We're using the second derivative as the derivative of the first derivative in order to employ the first derivative test. So what we want to do is find where this function is equal to 0 so that we can use those critical values to determine where the derivative is increasing, where it is decreasing, and thereby to find a maximum value. So we're going to set this equal to 0. And what that's going to lead us to is a couple of observations. The first is that this can never be 0 because a b e to the bx will never be equal to 0. So the only option that we have is that this here is equal to 0. Alright, so what I've done is I've set this factor equal to 0 and then subtracted b from both sides. And next I'm going to need to multiply both sides by 1 plus a e to the bx in order to get this x out of the denominator. So on the right side I'll then have a negative b times 1, which will be negative b, and then minus a b e to the bx. Alright, at this point I notice that I have these a, b, e to the bx's on both sides, and I realize, of course, that my exponent holds the variable that I'm solving for. And so I know that the only way to get this exponent out of, get this x value out of the exponent is to take the natural log of both sides at some point, because natural log of e to the bx is going to be bx times natural log of e. And of course natural log of e is 1, and so that will allow me to have my exponent outside. But before actually doing that, I notice that I can combine these terms here. So I'll add a, b, e to the bx to both sides. Now, I can do that, but if you just take a second, you'll notice that if I add 2ab e to the bx to both sides, that will give me a positive value over here. And then I could also add b to both sides, kind of just flip-flopping where they are going to be. And that will give me less negatives to work with, which is always nice. So I'm adding 2ab e to the bx to both sides and adding b to both sides. Alright, so at this point I'm in really good shape. I have an ab e to the bx, which came from adding 2 to a negative 1, and then I added b to this side. So I now can apply that. I can take the natural log of both sides, and I can do that now, or I could divide by ab on both sides first. I think that makes most sense, because then I'll have my e to the bx isolated. And of course, once I do that, I can cancel. B over b is going to be 1. So I'm left with 1 over a equals e to the bx. And at this point, I'm going to take the natural log of both sides. Okay? And of course, the natural log of something is the value that I must raise e to the power of to get get this value? Well, what must I raise e to the power of to get e to the bx? That's right, bx. So all this is here is b times x. Again, natural log of something is what I must raise e to the power of to get this something. Well, what must I raise e to the power of to get e to the bx? Simply bx. Then finally, to solve for x, I just have to divide by b or multiply by 1 over b. And so x is going to be equal to 1 over b natural log of 1 over a. And now I can go ahead and put my a and b values back into this function and to this equation to solve for x. And I'm going to want to use my calculator for this even when I do that. And so I'll have 1 over negative 0.0373 times natural log of 1 over 7.488. And I can hypothesize a little bit about what that should be. The natural log of a number, and this is going to be less than 1, what must I raise e to the power of to get something less than 1? Well, it's going to have to be a negative value because e is greater than 1. So this will be negative, and 1 over negative 0.0373 will also be negative. So I will get a positive value here. And I expect a remotely large positive value because 1 over 0.0373 is going to be a fairly big number. So let's go ahead and type that into our calculator and see what we get. All right, so I got 53.98 approximately, and I'm actually going to go ahead and just approximate this a little further. I'm going to say that x is approximately 54. We're talking about years here, so 53.98 is basically 54. Not that big of a difference. So now I have my critical point here, what will make my second derivative equal to 0. And so now I can make my second derivative sign chart. And my critical point is at approximately 54, and that's where that second derivative is 0. And I can go ahead and test out some values on either side of 54. Now I need to test them out in this thing here. Okay, I need to test them out in this thing. So this is not exactly the most fun to do, but at this point we've done quite a bit of work, and so I think we can manage with this last piece here. Remember, we only need the sign, so all we need to consider is the sign of this expression. So this will be negative. Now let's say we're going to plug in a value to the left. Well, that can be 0, right? And so let's do that if at all possible. So when we plug in anything here, this is going to be a positive in the denominator, and that's good. And then we'll have e to the 0. Well, e to the 0, anything to the 0 is 1, and so we'll just have a, b. Okay? And a is a positive number, and b is a negative number. So this will be a negative, this will be a negative. So I know when I multiply these two together, I'm going to get a positive value. Now over here, notice that I have a rational expression where I have a numerator and a denominator. I don't know for sure. None of these are being raised to an even power. So I can't say for sure whether either one is going to be positive or negative. And then I also know that I'm going to have to add this b value to it, or in other words, subtract 0.0373 from this value. And so, I mean, I could do a very good job of approximating this on my own, but it would probably be worthwhile to just go ahead and type this into your calculator. Because we're taking e to the 0, and that's just going to be 1, this expression is just going to boil down to negative 2 times a times b over 1 plus a plus b. So go ahead and type that into your calculator and see what you get. And if you do so, you should get a positive value, small positive value at that, and so it's important that we actually type that into our calculator. So we have positive. This is looking pretty good because this means that y prime is increasing. So remember, if something's increasing to the left of the critical point and decreasing to the right, then this will be a relative maximum value, and that is what we'd like to see. So at this point, let's go ahead and test out something to the right here, and you can try anything. I might recommend something like 60 or something like that. And again, if we do that, let's notice a couple of things here. The first is that this is going to be a negative value. Now the second is that this is also going to be a negative value because b is a negative value, and e to the negative whatever it is still going to be positive. So, it really doesn't matter. This is still going to be negative. So negative times negative is a positive. And then all you've got to do over here is actually compute this particular value with an x value of 60. So go ahead and try that out and see what you get. So if you did that correctly, you will get a negative value, and that means that y prime is decreasing on this interval. And what that tells you is that at 54, we have a relative maximum for our derivative. And remember, the derivative represented the growth of the population at any instant. And so that at 54 years after 1910 is when we're going to have a population growing at its fastest rate. Now, you might say to yourself, well, I need to check the endpoints, but you really don't, because the only endpoint that you have is at 0 here. And since y prime is increasing everywhere to the right of 0, there's no way that this is a maximum value, right? In fact, this would be a relative min. And so 54 years after 1910, we will hit a point of inflection, meaning, of course, that y, so if you think about our regular function, y, or the population, is currently concave up. And then at 54, it changes to concave down. And so if you imagine this graph, something like this, and right at 54 here is where the slope of y, this is y, this is where the slope is at its greatest value. It was increasing, right, concave up, so the slope was getting bigger, and then past this point, the slope's going to start getting shallower because it's concave down. So this is the point of inflection, and that is where the derivative is going to have its greatest value, in other words, where the population is growing the fastest. So our answer would be looking for an answer that talks about how the second derivative has a 0 at 54, meaning that 54 years after 1910 or 1964, the population was growing the fastest.